All right, today, by the way, when I listen back to my lectures over the years, I start every damned class the same way. I say, all right. And I can't stop. I don't know why. Talk about two topics today. First one, we talk about squares. If you're watching this on YouTube, you'll see two separate videos. So we've discussed procedures for dealing with a nuisance variable. Right, that's something you can measure, but you're not interested in its effect, you're just interested in removing its variance. That's a nuisance variable. So the way we've dealt with this so far is we've talked about blocking. I talked about the randomized block design, and that's the way you deal with it, and typically that's the way you're going to deal with this. And repeated measures, which are, in fact, a special case of a randomized block design. The ultimate nuisance variable is a single person being tested over and over again, and me knowing that different people are different. Right? So repeated measures are also simply a way of dealing with a nuisance variable. There's a statistical way to deal with it that we're not going to talk about in this course. You can learn all about it in graduate school, and it's called ANOVA. That's analysis of covariance. So what you do in that case is you statistically control for something. So you remove variance. You control for it statistically. When I'm going to start talking about it, I'm going to start teaching you about something that's beyond the scope of this course. So I'm not going to do it. So, but you can do that, and now and then you'll see someone in their honors thesis or something doing ANOVA. There's nothing wrong with it. It's a perfectly acceptable procedure. It's fine. We're not going to talk about this. We have talked about these two. What if you have two nuisance variables? So you've got an independent variable. That's your third variable. You have two nuisance variables. So you have two things you can measure that you know are going to cause a problem. But you can measure them and remove that variance. And you have an independent variable as well. And that's what you really care about. That's what you want to find out if there's an effect or not. So you have to find a way to sort of put them together. In fact, obviously, that's what I'm going to go with today. So if you put one row in a nuisance, put a nuisance variable in one row like usual, and then you put another one in the columns, and I'm apparently way too excited about this, note all the exclamation points. Look, this material's boring. I'm doing my best, all right? I can think back to one student of mine. I think I've supervised 98 honors thesis projects in my career. I think that's right. I counted it up when I applied for promotion a couple years ago. It's something like that. That was fun, by the way. You know how it works in academia? You don't just get promoted because you're good at something and your boss says, here's a promotion. You have to sort of literally reapply for your job. It's a lot of fun. So you write a 200-page document. It's great. You spend your whole down. I shouldn't do that. It's a very good job. But no one just walks up and says, hey, you want more money? But one of my students was looking at smells. And she was interested in, are people able to detect dangerous, noxious smells, which we are good at, right? But how well do they detect them if they're mixed in with non-noxious smells? So what if you had the smell of toluene, which is the stuff that's in contact cement? It's dangerous. There's a reason it's not good. And blueberries. Something smells good. So she had 8. Was it 8? Yeah. She had 8 different smells that were nice smells, 8 different smells that were bad smells. So she thought, how am I going to test this? am I going to need an 8 by 8 factorial design? So, and let's say you need 20 subjects per group. So suddenly she needs 320. Oh, there's not enough psych students. So there's no way she can do this experiment. But it's a really cool idea. And I said, well, why don't we put 8 of the smells in a row, 8 of them in a column, and then we'll just need to test a small number of people. In fact, we'll just test 8 people over different times. Actually, sorry, we'll test 16 different people. So you get something like this. This is on the rows and columns. So here's your rows, here's your columns. You have 4 different levels of one nuisance variable, 4 different levels of another nuisance variable, and I apologize for these being A's, B's, C's, and D's, because so far those have always been what? Different independent variables. Now they're just different levels of the independent variable. Put this over here for SAC. So A, B, C, and D are levels of a factor. They're levels of independent variable. They're not different independent variables. Each level occurs in each ordinal position. Note A occurs first, second, third, and fourth. B occurs second, first, third, fourth, and first. What did I say? Sorry, second, third, fourth, and third, etc. So like I said, these are pretty rare. I've had one student ever do these things, do one of these. Yeah, I forget what the other variable was, because she had nice smells, noxious smells, and there was something else that was actually the independent variable, and I can't literally remember what it is. I guess I had a supervised 100 honors thesis experiment. But instead of needing hundreds of people, she needed 16 people. Right? It's a really cool experiment. So each row and each column have one level each. This is called the Latin square. So Latin square because the Romans used to do these, they're basically kind of like math puzzles. They were kind of like classical era Sudokus, in essence. So that's why they're called Latin squares. So do you understand the design before we get any further with this? Because it is a weird research design. Like I said, it's a perfectly acceptable one. It's extremely rare that you run into it. And I professionally run into it once. And I'm old enough, my son turns 21 today, so I can tell you that I'm old. My daughter, who's visiting, is 28. I have children older than people in this room, and I've ran into this once. And I'm not saying that freaks me out a little bit, but it freaks me a little bit. Teaching intro psych in Newfoundland, I was 36 years old. I looked out and I went, "Oh my God!" I'm sorry, actually, I said, "Holy shit! I'm literally twice your age." And I just went back into talking. The time will come, and it'll be 3 times, and it's not far away. So you had an equal number of rows, columns, and independent variable levels. This is a very stringent kind of a set of assumptions, right? And then here's your model, which is any score equals the grand mean. These things shouldn't surprise you, the grand mean. Now, this is rows, columns, and levels of the independent variable. Okay, so any score equals rows, the grand mean, rows, columns, independent variable, and of course, error or residual, what's left over. This should tell you a couple things. Take a look at this model. Do you notice anything about this model that we should have to pay attention to when we're doing an analysis like this? Take a look. What do you see? Anything there that maybe is out of the ordinary? So while the model says rows, columns, independent variable, the model also doesn't know that rows and columns are nuisance variables. It just thinks of them as other sources of variation, if the model thinks at all, which is not way to think of it. But do you notice anything here? Jared, you look like you want to put your hand up. What do you want to say?
I'm in between where we don't have a interaction.
That's correct. That's one thing we're missing for sure. In fact, that's probably the big thing.
Yeah, I was going to say we're measuring a third main effect, but I don't know if that.
Yeah, but we have 3 variables.
Yeah.
Alpha, beta, gamma, but we would normally have alpha, beta, beta, gamma, alpha, beta, gamma. Yeah, that's all. We don't have those. We have no interactions. And you can see why, because to have interactions, you need every level of a variable occurring with every other level. This design is specifically made so you don't have to do that. Like I said, my student, Jen Sushro, didn't need 64 different cells, she needed 16. So she needed 16 subjects instead of, whatever that would be. Yeah.
So to put that together, we are using a design that purposely gets rid of all of the interactions so we don't have to worry.
Purposely, is one way to put it. It's a design that assumes there aren't any. So you have to be sure there aren't any, because the only place that error can go is over here, into the error, into the epsilon error. The only place it can go, as you can probably guess, we're going to test everything with epsilon. So if that gets bigger, it makes the f smaller, and we want a big F. So you want to make sure you have no interactions. And it's hard to know you have no interactions when you literally don't have a design that can show you interactions. Like, it can't show you them. And you can't even really get it through exploratory data analysis. So you better be just damned sure there aren't any. That's why you read the literature. If you read the past literature and see that these things ever interact and they don't, then you're fine. If there are interactions, it's going to make the error term bigger, which is going to make finding a significant F harder. So it's going to make, if there are interactions, you're going to be more conservative, which is nice, because at least you're not going to make a fool of yourself and say things that are there that aren't there. You might miss something that's real. So this is there's a reason I've seen it once in my career, and that's because it only works in extremely specific circumstances. The analysis of variance table looks like this. You've got 3 sources of variation: rows, columns, and the independent variable. And then there's something left over, we're going to call it residual. And the degrees of freedom work like this. You have p rows, p columns, and p levels of the independent variable. You have p minus 1 degrees of freedom for rows, columns, and IV. Your residual has p minus 1 times p minus 2 degrees of freedom. And your total is the number of observations minus 1, because that's always what it is. So if you ever see on a quiz, on a test, like the only thing left is the final, but if you see one that says rows, columns, independent variable, that's a Latin square. And you should look at that and say, I know that's a Latin square, now I just have to work out what the design looks like. And if I see that the p minus 1 is 5, well, that means and if these are all 5, 5, 5, and what would this be? This would be 5 times 4, so 20. Yeah, that's right. Well, it's got to be a 6 by 6 Latin square. There's nothing else it can do.
Sorry, the alpha was rows and beta was
columns. Yeah.
Thank you.
I mean, it doesn't really matter which, but yeah, that's the convention. So yeah, in that case, you'd have what? 5, 5, 5, 20, because 5 and then 6 minus 1 is 5, 6 minus 2 is 4, 5 times 4 is 20. 5, 10, 15, 20, 35, and we'd have 36, because it'd be a 6. Yeah, that's right. So you look at that right away and say, that's a Latin square. Now, we're very tempted to always go A, B, C, D, and then shift it over, but that's only one possible square. So how do you choose the Latin square you use once you know the dimensions? 4 by 4, or like Jen's 8 by 8. there are tables of Latin squares, like they exist in the back of certain textbooks, and they exist on the internet, and you can just find a random Latin square and use that. So I'm showing you the one that just goes A, B, C, D, E, or whatever, and then we shift the E over here, goes E, A, B, C, D, etc. But it doesn't always have to work that way. It's as long as each level occurs in each ordinal position. So there's a lot of different possible squares, so you choose one randomly typically. As I said, these are 2 quick ones today. Sort of just mopping up at this point. Mopping up analysis scenarios. So these can be really useful designs if you meet their very stringent assumptions. So like I said, you can look it up if you want in the library. The honors thesis experiment done by Jen Sushro in about 2007, maybe 2008, something like that. Quite a while ago. And her design met the, so we said, yeah, let's just use a Latin square, what the hell? So she did an 8x8, she had 16 people instead of like an 8x8 Latin square, instead of an 8x8 design with 64 cells. Let's say 20 subjects per cell, suddenly we need more subjects than we have students at the university. So we couldn't have done the experiment any other way. There have to be no interactions. Jen did a lot of reading and found out that no, the variables that she was interested in didn't tend to interact. They were, quote, additive, as we say. So there's no worries. So an equal number of rows, columns, and levels of the independent variable. But if you have those, your goal. These are really good designs. Unlike the hierarchical one I talked about last week, which is like, just don't do this. Unless you have to. This is fun. Chances are, though, you're going to run into it hardly ever. Now you could have something where you have enough sub. Let's say you have a 5x5 Latin square kind of setup, but you have, so 5x5 gives us what, 25 observations. Let's say we have 50 people. You could actually do 2 squares, and then you have, this is where it gets really weird, you'd have rows, columns, independent variable, error, but you'd also have squares. You have 2 degrees of freedom for different Latin squares, which is kind of like, that's something more theoretical. You can also have a cube. But again, this is the kind of design that this is the kind of design that shows up in graduate textbooks to confuse you.
It's black.
And then you use Hebrew letters for the depth for some reason. And that's a Greco-Latin square, that one's called. And then there's the hyper-Greco-Latin square, which actually is 4-dimensional and you can't imagine it. Statistics books are great that way when you get to graduate school. You look at that and go, is this ever going to happen? No. Okay. All right, questions about Latin squares? Don't worry about hyper-Greco-Latin squares. I'm just telling you those things exist. All right, good stuff.